Hey Phys 1 kids, Campbell here. Welcome to your very first video. In this video, we're going to talk about verbal descriptions of motion. That is, we're going to talk about the vocabulary that you're going to be using for our first 2 units. Now, a little bit of background. For our first 2 units, we're just going to be studying motion, but not what causes the motion. We're going to move to that in the 3rd unit. We're also in this unit only going to look at one-dimensional motion, which means we're moving in a straight line. Even though I know we usually don't just move in a straight line, we're going to simplify things for our first unit and just look at going straight. We're also going to use what's called the particle model. Now, if you think about objects in motion, like you, right? You have limbs that are moving when you're moving, and organs and molecules, or you're in a car, right? And then there's you and the parts of the car, and all these things are moving. And instead of looking at individual pieces within that whole system, we're going to treat everything as just one object, and we're going to simplify it. And it makes our approach to one-dimensional motion much more simplified. And you'll see simple is good. All right, so let's get into it. From a definition standpoint, the first thing you need to know is the difference between a scalar quantity and a vector quantity. A scalar quantity is something that we only express using a magnitude, which means a number associated with a unit. So like distance, speed, those are scalar quantities. But vectors are quantities that are expressed with both a magnitude and a direction. So you're not just going to give me a number and a unit. You're going to give me up, down, left, right. When we get to 2-dimensional motion, you'll give me an angle, maybe 30 degrees north of west. We can even use positives and negatives to indicate direction, and we'll talk more about that later. But a good example of a vector is something called displacement or velocity. And if you're a Despicable Me fan, then there's always this.
Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
Oh yeah! So let's talk about some different scalar and vector quantities. So we're going to start off with positioning information. The definition in physics of position is where you are with regard to some origin at some particular instant in time. So how many miles away are you from where you started, or how many meters? So it's a location, whereas distance is a change in a position. So it's the length of the path traveled by an object. Now, distance, which we symbolize as a delta x, is a scalar quantity. So you only talk about how far did you go just from a quantity standpoint. So if you go back and forth, you just add all those up. It's the total length of the path. That's different from displacement. Displacement, which of course is also a delta x, but we put this little arrow above, that symbolizes that it's a vector. And what it is the change of the position of an object from the initial position to the final. Or if we calculate it, it's always final minus initial. But so to look at our final position, and we subtract our initial position, and that gives us the displacement. Displacement is also a vector quantity, so you just don't give a magnitude, you also have to provide a direction. Now, if you take a look at our picture here, you'll see that, say you're driving down the street, and maybe this is your initial position. Maybe there was a stoplight. I don't know, that would be a weird place to stop, wouldn't it? Maybe you had to catch a Pokemon. And you travel another 100 feet. Then this would be both your distance and your displacement. When we calculate our final minus initial, right, it'd be 150 minus 50, which is 100 feet. But that's also our distance, because that's the total path we have taken. However, say you turn around and go back part of that way. Now the distance is 150. You went from 50 feet out to 150 feet and then back another 50. So our distance now is 150 feet, but your displacement, final minus initial, right, would be 100 minus 50, which is 50 meters. But you are to the right. So when we talk about displacement, in our first case, we were 100 feet to the right or to the east. And in our second scenario, we are 50 meters to the right or east of our initial position, even though we've come back a little. So make sure you know the difference between distance, total path taken, displacement, the difference between where you started and where you stopped, and position, just where you are with respect to some coordinate system. Another difference that you need to understand is the difference between speed and velocity. Now, they're similar in that they're both the rate of change of position, right? They're like, how fast are you going? And their SI units are meters per second. We always work in SI units in physics. So while maybe I talked about feet on the last slide, we'll always talk about stuff in terms of meters or kilometers. What's different about them is that speed is the rate of change of distance, so that total path over time, whereas velocity is the rate of change of displacement. So it's the final minus the initial. Also notice from a symbolic standpoint, they're both V's, but velocity again has that vector arrow. And I'm going to just apologize now. There are times where I will be talking about velocity and I'll make the symbol V and I won't put an arrow above it. So sorry. Now, like I said when we talked about vector and scalar, speed is a scalar quantity. The equation for it is distance over time. So the total path divided by the time it took to do that path. But you just give me a magnitude and meters per second. Whereas velocity is the displacement, that final position minus the initial position divided by that change in time. But you also need to give me a direction. So maybe it's 50 meters per second to the right. Now, if you read this sentence, Sam and Sally are watching a jogger compete in a 400-meter lap in 100 seconds. Sam states the jogger's velocity was 4 meters per second during the lap. Sally objects and says, no, the jogger's speed was 4 meters per second. Who's correct? What do you think? Well, I mean, 4 meters per second is definitely the rate of change. It's definitely the speed, but if they're making a lap, right, the tracks are circles. So if they make a lap, right, they are getting back to where they started from. So while maybe the distance is 400 meters, what's the displacement? Well, if you end up back where you started, your displacement is 0, which means the velocity is actually 0. What? But your speed's not, right? Your speed is definitely 4 meters per second. So of course, Sally wins. Now, from a calculation standpoint, if we look at an average speed or an average velocity, and here we have a runner that's running 200 meters east, then changes direction and runs 300 meters west. If we look at the average speed, right, we would just take our total path, which is that 200 meters to the east plus another 300 meters to the west, so that's 500 meters, and divide by 60 seconds, which gives us an average speed of 8.33 meters per second. Again, direction doesn't matter because it's a scalar quantity. But if we look at the average velocity, how is it different? Well, remember, we're looking at final minus initial. So if we say that she starts at 0, and the final position, she went out 200 meters, and then she went back 300, right? Our final position is going to be a negative 100 meters from where she started. So we need to pay attention to the direction an object's moving. I go out 200 meters in one direction, we'll call that positive. I go back 300 meters, so we'll call that negative, which leaves us with a total displacement of a negative 100 meters from where we started. So we divide that by 60 seconds, and now we get a negative 1.67 meters per second. The negative means it's to the left of where we started. We could also call that west because we started with positions of 200 meters to the east and 300 meters to the west. So our average velocity is 1.67 meters per second to the west. Make sure you have a magnitude, a unit, and a direction. Now, when you're running, right, if you start off, right, you're starting at rest and you're increasing your speed, and maybe like if you turn around, right, you've got to slow down and turn around. So there's a difference between an average velocity, which is the average speed that you've gone, or sorry, not average speed, but the average velocity. So it's just an overall average of all of the different speeds that you went. And that's just that displacement divided by time. If we're talking about speed, it'd be just distance over time. Whereas instantaneous velocity is the velocity at a particular instant in time. So when you first start accelerating when you're running, right, your velocity is changing. So at any different particular moment in time, you may have a different velocity. So we say that that's the velocity as the limit of time approaches zero. Now, we're going to get more into that when we talk about graphs in our next video. And sometimes objects will be moving at constant velocity, so the instantaneous velocity and the average velocity will be the same the entire time. However, there are times where the velocity or the speed of the object is changing, and that means they're going to be different. And that's going to be important when we get to calculations and when we get to graphs, because it's easy just to do the change in position over change in time for the entire segment of motion. It's harder to think about different changes and what those different increments of velocity are. But we'll talk more about that in the next video. Now, positives and negatives in physics, this is a big thing because in math, they're about magnitude, or, are you below zero? Is your number smaller? In physics, it's about direction. So anytime we talk about the positive direction, we're going to be talking about something moving up or something moving to the right in the positive x direction. Negatives in physics are if an object is moving down or if an object is moving to the left, which is negative x on the negative x-axis. This is important because positives and negatives are important from a direction standpoint, but they are important from a math calculation standpoint. So let's talk about positives and negatives in physics. From a position standpoint, a positive position would be to the right or above the origin, whereas negative would be to the left or below. Displacement is very much similar to that. A positive displacement, again, would be to the right or above your initial position, and negative would be to the left or below your initial position. So it's about where did you start? It's a reference from where you started. Velocity is the one that'll mess you up because kids seem to think that a negative velocity means I'm slowing down. That is not true. Velocity is positive if you are moving in the positive direction, which means you are moving to the right or up. A negative velocity is if you're moving in the negative direction, which would be to the left or down. So velocity signs are not about speeding up or slowing down. It's about which way are you moving. Last topic is acceleration. So acceleration is the rate of change of velocity. It is a vector quantity. So it's the final velocity minus the initial velocity divided by that change in time in which the velocity change happened. The units are meters per second squared. Now, this is a tricky one. Acceleration can be positive or negative depending upon both the direction of motion and if an object is speeding up or slowing down. Your brain wants to say that if you have positive acceleration, you're speeding up, and that if you have negative acceleration, you're slowing down. And sure, that's true. Positive acceleration is if you're speeding up in the positive direction. If you've stopped at a stop sign and now you accelerate away from the stop sign, if you're moving in the positive direction, that's positive acceleration. But you can have positive acceleration be slowing down. In fact, if you are slowing down in the negative direction, that's positive acceleration. What? So it's not about speeding up or slowing down. It's a combination of speeding up and slowing down and what direction you're moving. So what I like to do is I like to call speeding up positive and slowing down negative. And from a math standpoint, right, if you multiply a positive number by a positive number, it's positive. But if you multiply a negative number by a negative number, it becomes positive. So slowing down, which is a negative, in the negative direction, negative. Negative times negative is a positive. So that's one way you can remember that slowing down in the negative direction is actually positive acceleration. Oh. Negative acceleration is slowing down if you're moving in the positive direction. So the things that your brain wants to say about positive and negative acceleration is true when you're moving in a positive direction. But you can have negative acceleration and be speeding up. As long as you're speeding up, in the negative direction. So when we switch to the negative direction, going left or down, then our signs of positive and negative acceleration are going to mess with you. So negative acceleration, slowing down in the positive direction, but speeding up in the negative direction. Anytime you multiply a positive number by a negative number, it becomes a negative number. So that's another way to think about the signs of acceleration. And I will see you in class.